Hi, I'm Zifan Nan, and I'm a fifth-year PhD student from North Carolina State University. Thanks for attending my presentation. The topic of my presentation today is enabling near real-time natural language understanding-driven natural language programming. So natural language programming refers to a problem that, given a natural language queries as specification, the code synthesizer should automatically generate the code expression that fulfill the intent of the original natural language queries. So for example, in text editing domain, the English query could be insert a colon at the start of each line, and the code synthesizer should take this sentence as input and automatically generate the code expression at the right side of which can directly do the insertion work as required by the English query. So why do we do natural language programming? There are two purposes. So for general users who does not know how to program, the best way or the most convenient way for them to express their needs is through natural language. For example, in a smart home, they can just say turn on the light to operate the lights, and in text editing domain, they can just express their needs, and then we can directly generate the codes and process the code and run the code to perform the job as required by the natural language. Then for programmers, if they're trying to learn a new domain with a lot of APIs, for example, an HTML domain in LLVM with 500 APIs, it's very hard for them to remember all the details about the APIs. So they always need to refer to the documentation we're trying to write in the code expression in this DSL. However, if we have a natural language programming tool as shown below, which can directly take the natural language query as input and synthesis the corresponding code expressions and then directly put the code expression into the source code, it will be very easy for them to program in new domains. So the current natural language programming techniques are focused on a data-driven approach. This approach will rely on a lot of labeled input code pairs training data. So for example, in a former RNN model that was trained to synthesize bash scripts, it collected more than 5,000 natural language bash script pairs. And another famous alpha code, which is claimed to achieve the average human programmer level, it is trained on a transformer with more than 700 GB of code. Recently, another way of natural language programming called natural language understanding-driven approach is proposed. This approach is inspired by pure human programming. It is driven by the natural language understanding and built up on the understanding both description of the API and the user's queries, and then assemble the APIs based on the DSL grammar. So this method requires no training data. So there are two advantages of an NL-driven approach compared to the data-driven methods. So the NL-driven approach, it avoids difficulties and cost in collecting a large number of training samples. And then if we're making changes to the target DSL, the data-driven method may need to collect more data about the new changes and retrain the model, but the NL-driven approach, it just need to update the documentations, and then it can easily adopt it to the updates. However, the current NL-driven approach is slow. When synthesizing 200 cases in text editing domain, 38% of the cases they need more than 1 second, and around 18% cases need more than 20 seconds. While within those 20-second cases, 5 of them are not finished in up 20 minutes. From the usability engineering book of Jacob Nelson, there's a sentence that 10 seconds is about the limit for keeping the user's attention focused on the dialogue. Therefore, with the current performance, the NL-driven approach is not practical for use in the real programming situations. Therefore, in this paper, we're trying to solve this problem. So we first offered a systematic study on the efficiency issues of the NL-driven approach, and then we propose a novel algorithm called dynamic grammar graph-based translation, and then we also introduce two new optimizations, which they can help optimize the synthesis process. And then we also use a set of experiments to demonstrate the effectiveness of our proposed solution. So first, let's look at the NL-driven approach. The NL-driven approach, it first take the query as input and put it inside a dependency parser. The dependency result will show us the relations inside the information of the words, between the words. And then this information will be transformed into a dependency graph, and we only keep the key information inside the original query. So we'll prune out the unnecessary informations. Then for each node inside the dependency graph, which is a keyword inside the query, we'll find the candidate APIs based on their descriptions, natural language descriptions. If the keyword and the natural language descriptions are semantically related, then we choose that API as a candidate for this keyword. Then the first step is transform the age inside the dependency graph into the path in the grammar graph. So grammar graph is a graph representation of grammar. So then for each candidate inside the node of the dependency age, we'll try to find a path in grammar graph that can connect the API inside the node of this age. So then the path in the grammar graph, so from the code perspective, the semantic of this path are equivalent to the semantic of dependency age inside this dependency graph. So they both show the relations of this insert. Let's see, this insert and string, if we take the number 2 age as example. And after we find all the path candidate for each age inside dependency graph, we will create combinations for all these paths with one path from each age, and we will merge them into a code generation tree, which is a tree representation of the final code expression. And then we will use the tree with the minimum number of API as our promising candidate, and then translate it into the final code expression. That's how NL-driven approach works. But then we can look at the example which can show us that the path merging step actually has a very high time complexity. So because Hyson will enumerate all combinations, then we can assume the whole dependency graph has L level, and then it has E dependency age in each level. Then for each age, it will have P path candidates, and then inside each level, the combination will be P to the power of E. And then for the whole dependency graph, if we want to try every combination, the final path combinations will be the production of each level, which is the production of P to the power of E. So the overall complexity is very high. And let's see, if we have 4 levels and each level has 4 ages and each age has 4 candidates, then there will be more than 4 billion combinations, which is very inefficient. So let's take a look at a running example. With the same dependency graph, and the age 1, 2, 3 both have 2 path candidates. Then the total combination is 8 combinations. But if we're looking at those combinations, there are redundant computations. Then can we just reduce these redundant computations? When we look at the dependency graph and trying to merge their paths, actually there are 2 kind of path merging steps. The first relation is parent-child relation. So like age 2 and 5 here, when we merge the paths from this 2 age, we just attach the head of the child path to the tail of the parent path. Then another relation is sibling relation, like 2, 3, and 4, H2, 3, and 4. When we merge them, we're actually doing the common prefix merge in each level. Therefore, if we can find the optimal partial CGT for a single layer, and then we grow it from bottom to up layer by layer, then if we only keep track of the optimal partial CGT, we can end up getting the final CGT when we reach the first level. So based on this idea, we create the bottom-up dynamic grammar graph translation, which is also called DGGT algorithm. So the first step of the DGGT algorithm will add all APIs that is mapped by the leaf nodes of the dependency graph. For example, the semicolon here and the start from and line scope starting start from are for the API for the keyword start. And then we'll move on for the bottom level. So we'll create the minimum partial CGT for bottom level. We'll create a node that represents the string, and then it will record the minimum size and where this minimum CGT come from. And then for the middle layer, which includes 3 edges, we will try different combinations within the layer and merge them. And we only keep the optimal partial CGTs for different combination of the root and the leaf nodes. So for example, with 4 edges of H2, with 4 paths of H2 and 3, we should end up with 4 partial CGTs, but with the same root and leaf nodes, we only leave the partial CGT with minimum size, and inside the root of this this partial CGT will record it like the minimum size of a current partial CGT, and then we process to the first level, and we in the first level in the root with the 4 more optimal result applied, we can get the actual mean size of the final CGT, and we can retrieve the tree based on the record in each node. So after retrieve the dynamic graph, we have the code generation tree with a minimum size, and then it will be directly translated into final code expression, which will be the return of the synthesizer. So besides this DGGT algorithm, we also have 2 other optimizations. The first optimization is called grammar-based pruning. So this is based on the observation of a of the production rules of a grammar. So inside a grammar, a non-terminal, when we apply the production rule of one non-terminal, only one production rule should be applied to this non-terminal. Therefore, if 2 paths that will be merged, like inside one combination, it comes 2 production rules for the same non-terminal, they must be grammarly conflict. So for example, here in these 2 paths, they both derive from the non-terminal poles, and therefore the H2.2 and the path 2.2 and path 3.1, they are conflict. Therefore, we do not need to do the prefix merge at all. We can directly skip this combination. And the second optimization is called orphan node relocation. This happens when the dependency graph gives us the error edges. So then this edge will end up with no candidate path that can actually connect the 2 nodes, the 2 nodes of this dependency edge, which means the governor is not the real governor of the dependent. So the dependent is then called the orphan node. And then when we do the path finding, it ends up finds all the paths from the dependent from the orphan node to the root node in the grammar graph, which will end up with a lot of path candidates. So we relocate this offer node as a dependent of another node. We call it K if this NK is inside the candidate path of NJ. So we'll check the path. And if, let's say here, insert could be the parent of line, then we'll create edge that link these two nodes. So after applying the DGGT algorithm, with our running example, we only need to combine, we only need to do 4 combinations in the second layer, and others we just do the attach, we just do the attach merge. And then for the algorithm level, the complexity for each level is still p to the power of e, but when drawing the partial optimal CGTs into the optimal final CGTs, the time complexity becomes only the sum of p to the power e, which is much better. And then the true optimization method further reduce the cost. So we conduct a set of experiments to prove to give us answers to these 3 questions. So first one is how the efficiency benefit can the technique bring to the NLU-driven methods, and then does the new algorithm affect the synthesis accuracy? And then the third question is how much does each of the optimizations contribute to the speedups? We conduct our experiment in 2 data sets and in 2 different platforms. One is the normal laptop and another is server machine. And we use synthesis time, speed up, and accuracy to evaluate as an evaluation for the performance. So first, let's look at the efficiency benefit. So from the mean value, we can see the speed up bring by the DGGT algorithm is from 25 to 32 in estimation domain and more than 100 in text editing domain. And from the intervals, different time intervals in the percentage of cases in those intervals, we can figure out that more cases have dropped in the within 0.1 seconds in both domains compared to Hising. And when we see the accumulated execution time, we can see that with number of cases growing, the sum of the execution time of Hising grows much more than the DGGT algorithm. And when we look at the synthesis accuracy, the synthesis accuracy is also approved with the DGGT algorithm applied. So theoretically, the DGGT algorithm should produce the identical synthesis result, but the timeout cases are also considered error here in this experiment. So the DGGT has fewer timeout cases, hence it has higher accuracy. And then for optimization benefits, we conduct a case study to check out like the benefits of each step. So from original Hising, let's take the number 4 case as example. From original Hising, there are 800 paths inside 6 edge, and there will be 2 billings of path combinations. But after the orphan relocation, it reduced the path number to around 100, and then it ended up with 200,000 combinations only. If we calculate by the sum with the layer, and then the grammar-based pruning further remove a very large portion of the rest of combinations, which has the grammar conflict, which only left 86 combinations that actually needs to be merged. Then in this case, the original query didn't, and the original Hising method didn't finish it within 20 minutes. So which gives more than 2,700 speed up in this case. So in conclusion, this work presents the first known solution that enables near real-time NL-driven natural language programming. It introduced a new algorithm and 2 optimizations to reduce the search space and address the complexity from queries, and our experiment further demonstrate the effectiveness of the proposed solution. So that's all about my presentation. Thanks for listening. Feel free to contact me if you have any questions.